Welcome everyone to a new virtual seminar on geometry with symmetries. Today, it's my great pleasure to welcome Broder from UQ, uh, and he'll be talking about invariant metrics in complex analysis and the conjecture of Kobayashi and Lang. Welcome, Kyle.
Thanks, Ramiro, and thanks for the invitation. And of course, thank you everyone for taking the time to listen to me talk about something that I have been obsessed with for a very long time. I should say that the title is a little tongue-in-cheek in the sense that invariant metrics are not what probably everyone in this audience thinks is an invariant metric. And in fact, the main objects of interest in this talk are going to be largely highly non-symmetric objects. But nevertheless, I hope everyone finds the topic very interesting.
We forgive you.
Thank you, Ramiro. So the results of this talk are based on a joint work with James Stanfield, who's in the audience. And much of the exposition that's presented here will appear in an upcoming work with Frédéric Campana and Hervé Gaussier. So let me start very classically, but interpret the results with about 100 years of developments and insights. So the model of hyperbolicity will always be the unit disk in the complex plane. Now, the unit disk has a number of remarkable properties. The first is that every holomorphic map from the complex plane into the disk is constant. The second is that there's a complete metric on the disk whose curvature is bounded above by a negative constant. The third is that there's a distance function in the sense of, first-year analysis, a symmetric positive function that satisfies the triangle inequality. But there's a special type of distance function on the disk, namely one for which the automorphisms of the disk, an automorphism here is understood to be a biholomorphism, so an invertible holomorphic self-map, together with the property that a holomorphic, if you have any holomorphic self-map, then this distance function decreases under pullback. In other words, such holomorphic maps are Lipschitz with respect to this distance function. The fourth property is that if I look at a compact Riemann surface, so let's call that a curve, say S, and I look at the canonical bundle. So the canonical bundle in this case is just the cotangent bundle. So I take the holomorphic cotangent bundle. Then the canonical bundle or cotangent bundle of such a compact Riemann surface is ample if the universal cover is the disk. Now, what that means, I'll describe this in greater detail in a moment, is that I can use the sections of some tensor multiple of this bundle to holomorphically embed the curve into some complex projective space. And this goes back to Poincaré in 1882, I believe. The notion originates there. So, of course, statement one is classical. That's just the classical Liouville theorem from one complex variable. This metric that's given in statement two is just the Poincaré metric of constant negative Gauss curvature. You can normalize it to any negative constant you like, typically -1 or -4. The distance function in statement three is given by integrating the metric in statement two. In other words, by defining a distance function by declaring the distance between 2 points to be the infimum over the lengths of curves measured with respect to this metric, this negatively curved metric. And the properties of this distance function, namely the fact that automorphisms are isometries and holomorphic self-maps are Lipschitz, that's a consequence of the Schwarz-Pick lemma. Finally, statement 4 is just a consequence of the Riemann uniformization theorem together with Riemann-Roch. So each of these properties have been used to define classes of hyperbolic complex manifolds. So we'll say that a complex manifold X is Brody hyperbolic if every holomorphic map from the complex plane to X is constant. We'll use this ad hoc terminology that a complex manifold is negatively curved if there is a Hermitian metric with holomorphic sectional curvature bounded above by a negative constant. Now, I don't expect anyone to understand what the holomorphic sectional curvature is, so I'll explain this in significantly greater detail in a moment. But for the Riemannian geometers, this is rather easy to understand. Let's say for a Kähler metric, this is the restriction of the sectional curvature to the two planes that are invariant under the complex structure. So it's a natural curvature condition to consider in complex geometry. We'll say that a complex manifold is Kobayashi hyperbolic if the Kobayashi pseudo-distance is non-degenerate. That I also will explain momentarily, but I will get away with actually never defining it in this talk. I'll never need to define it. And finally, we say that a compact complex manifold in this case is canonically polarized if the canonical bundle, which is given by so it's a holomorphic line bundle given by the top exterior power of the holomorphic cotangent bundle, if that is an ample line bundle. In other words, if we can use the sections of a tensor multiple of the canonical bundle to holomorphically embed into some complex projective space. Now, although, well, arguably definition 1 is the simplest, but that actually appeared last. So that's due to Brody in 1978. The holomorphic sectional curvature of a Hermitian metric appears to first be introduced by Bochner in 1947. Grauert and Ricci showed using the Schwarz lemma that 2 implies 1. So if you have a negatively curved Hermitian metric, it doesn't have to be complete, but so long as its holomorphic sectional curvature is bounded above by a negative constant, then the Schwarz lemma argument, well, the Schwarz lemma implies that every holomorphic map from the complex plane has to be constant. The Kobayashi pseudo-distance was introduced by Kobayashi in 1968, and the Kobayashi pseudo-distance is, well, firstly, let me tell you what a pseudo-distance is. It's exactly a distance function, but you drop the non-degeneracy assumption. So it's symmetric, satisfies the triangle inequality, but the distance between 2 points may be 0. And the remarkable thing is that any complex manifold admits a Kobayashi pseudo-distance, and a very rich notion of hyperbolicity arises when you mandate that Kobayashi pseudo-distance is non-degenerate. So the Kobayashi pseudo-distance is an example of an invariant pseudo-distance, or an invariant metric, which is understood to mean that automorphisms are isometries, and that it possesses this decreasing property, namely that if I have a holomorphic map between two complex manifolds, then when I pull back the pseudo-distance on Y, that's less than or equal to the pseudo-distance on X. Now, since the Kobayashi pseudo-distance on the complex plane vanishes identically, so it's everywhere degenerate, if I take the contrapositive statement, so I assume that my manifold is not Brody hyperbolic, in other words, I assume that I have a non-constant holomorphic map, then by pulling back and using the decreasing property of the pseudo-distance, I see that I can't be Kobayashi hyperbolic. So in particular, Kobayashi hyperbolicity implies Brody hyperbolicity. But remarkably, if the manifold is compact, they're equivalent. And this is one of the reasons why Kobayashi hyperbolicity is one of the richest. There are many pseudo-distances one can introduce. Carathéodory pseudo-distance is a Wu pseudo-distance, so forth. Kobayashi hyperbolicity is particularly favorable because of this link, because algebraic geometers can attack questions of the existence of holomorphic maps from C, but it's much harder to attack the pseudo distance directly. So the fact that we have this equivalence is a very big deal. So the L4-Schwarz lemma argument does not show that 2 implies 3, but it was later shown by Green and Wu that you can deduce from the existence of a negatively curved metric, the Kobayashi hyperbolicity. Obviously, compactness is not assumed here, nor is completeness, but you need a much more complicated argument, and you need to estimate the Kobayashi pseudo distance directly. Now, concerning 4, as I've said, I think 2 times already, but it's worth repeating, that the canonical bundle of a compact complex manifold is ample if, when I tensor the canonical bundle with itself sufficiently many times, by evaluating the sections at each point, the associated map defines an embedding into some complex projective space. Now, these are these manifolds admit a very rich structure. Firstly, they're projective, i.e. submanifolds of CPN, and therefore methods of algebraic geometry are readily available. But as a consequence of the Orban-Yau theorem, they also admit distinguished metric structures, namely they admit Kähler-Einstein metrics with negative Ricci curvature. On the other hand, it's clear that condition 4 is the weakest in the sense that 4 does not imply any of the others. And the standard, in fact, only example anyone ever brings to mind is the Fermat hypersurface. So you look at a hypersurface in CPN locally given by an equation of this form. And if the degree of this hypersurface exceeds n+1, then the adjunction formula tells you the canonical bundle is ample. On the other hand, you can actually explicitly write down some rational curves, and in particular, you can produce holomorphic maps from C into this. And so it can't be Broder hyperbolic, let alone any of the other notions of hyperbolicity.
So Kyle, just to
yes,
summarize if I understood correctly. So the first 3 are believed to be equivalent, or maybe you told us they are equivalent, or there's some missing implication. How does that work?
Yeah, so exactly. Yeah, so 1 and 3 are equivalent for compact. Let's assume
implies,
compact.
Yeah.
2 is the strongest at the moment.
I see.
Now, it turns out that it was conjectured for a very long time that 1, 2, and 3 were all equivalent for compact manifolds. But in 1997, Demae produced an example of a Kobayashi hyperbolic that doesn't have a thing. So it's actually not the negative holomorphic sectional that's equivalent. It's actually this non-degenerate K-jet curvature for some K, and it's a bit more complicated.
Okay.
The main idea here is that holomorphic sectional controls all the jets of a entire or a holomorphic map, while Kobayashi hyperbolicity is conjectured to only be related to the jets of some order. So,
and they all imply ample canonical bundle.
That's the question. Do they imply ample canonical bundle?
Oh, okay.
So ample canonical bundle doesn't imply anything else.
No.
Yes. The question, the main point of this talk will be whether the reverse implication is true.
Thanks.
Okay, so as I alluded to before, since I'll be primarily concerned, in fact, exclusively concerned with compact complex manifolds, I never have to define the Kobayashi pseudo distance. And out of convention, I would just say that a compact complex manifold is Kobayashi hyperbolic if every holomorphic map from C into X is constant. So I'm equating Kobayashi and Broder hyperbolicity. Some key examples to keep in mind: compact quotients. If you have a bounded domain in Cn, call it omega. You take a compact quotient, then that will be obviously Broder hyperbolic and therefore Kobayashi hyperbolic. So in particular, ball quotients are, compact ball quotients are Kobayashi hyperbolic. A generic smooth hypersurface of degree at least 16n cubed times 5n plus 4 in Pn plus 1 is Kobayashi hyperbolic. This is related to a general conjecture of Kobayashi where he predicted that if you take a general hypersurface of sufficiently large degree, such that the lower bound on that degree depends only on the dimension, then it will be Kobayashi hyperbolic. And the best known result in this direction is when that lower bound is 16n cubed times 5n plus 4. And that's this 2023 result. Earlier results are obtained where the lower bound was not effective, and then some people worked very hard to get effective bounds. Now, it's, of course, as we saw from the Fermat hypersurface, you have to take it to be a generic hypersurface. It doesn't hold for all hypersurfaces because you can just take a Fermat hypersurface of this degree. And once you have a Kobayashi hyperbolic manifold, it's not difficult to proliferate them. Namely, Kobayashi hyperbolicity is inherited by products, submanifolds. So if I take a complex submanifold of a Kobayashi hyperbolic manifold, it will remain Kobayashi hyperbolic, and universal covers. So the main purpose of the present talk is to provide the most general evidence for the following conjecture of Kobayashi and Lang. And Kobayashi conjectured this in 1970, and it was independently conjectured by Lang in 86. The conjecture is the following. So I suppose that I have a compact Kobayashi hyperbolic manifold, and I suppose in addition that it supports a Kähler structure, which I'll remind everyone of the meaning of that in a moment. Then it's predicted that the canonical bundle is ample. So the weakest of these conditions is actually honestly intended to be weaker in the sense that 3 should imply 4, referring back to the dot points I had before. Now, this is, on the face of it, frankly ridiculous, because all you're asking is that there are no holomorphic maps from C into the manifold, and you think you can get a projective manifold with a Kähler-Einstein metric out of that. So it's, on the face of it, very bold, but I mean, after a while, you understand the condition of no entire curves or no holomorphic maps from C into the manifold is extremely restrictive. So for those who have not been completely enamored by Kähler structures just yet, so it's a compact, or not even compact, a complex manifold X is Kähler if it admits a Hermitian metric G for which the 2 form given by inserting the complex structure into the first argument of the metric, that will define a non-degenerate 2 form. If it's Kähler, if it's a closed 2 form. So in other words, this omega defines a symplectic form. Now, if that's not particularly appealing to you, then this is equivalent to the Levi-Civita connection being compatible with the complex structure in the sense that the complex structure is parallel with respect to Levi-Civita. Now, the main thing about Kähler structures is not their properties or anything of that type. It's the fact that they exist at all, and even more absurdly, they exist in abundance. So the model spaces, namely the Euclidean metric on Cn, the Bergman metric on the ball, and the Fubini-Studi metric on Cpn are all Kähler. So now, since Kähler structures are preserved by submanifolds, by complex submanifolds, we know that the complex submanifolds of Cpn and the complex submanifolds of Cn are Kähler. So all projective manifolds support a Kähler structure, and all Stein manifolds support a Kähler structure. So they exist in absurd abundance. So this is the conjecture that I'm most interested in. If we look, so we've already seen in the first slides that in dimension 1, everything is equivalent. In dimension 2, this goes back to Wong in 81 and Campana in 91 independently, and they verify the Kobayashi Lang conjecture for compact complex surfaces using the Enriquez-Cadara classification. So you essentially look at the list and then progressively knock off the ones that don't have ample canonical bundle. And the key here is actually to rule out the hyperbolicity of K3 surfaces. So K3 surfaces are Ricci, simply connected Ricci flat Kähler manifolds in complex dimension 2. And the key point there is actually to deform. You have to use a deformation argument. You deform to a nearby Kuma surface. A Kuma surface has a bunch of holomorphic maps. And since Kobayashi hyperbolicity is preserved by deformation, you can't have a K3 surface being hyperbolic. So that this role played by these Ricci flat Kähler manifolds persists in higher dimensions. And in fact, for compact Kähler threefolds, so in the next dimension up, the Calabi-Yau threefolds or the Ricci flat Kähler threefolds are the only remaining case. So due to the very impressive work of Wilson, Heath Brown Wilson, Peter Nell, and others, it suffices to rule out the Kobayashi hyperbolicity of Calabi-Yau threefolds with second Betti number less than 13. But the most recent and significant and rapid progress over the last couple of years has come from differential geometry, where we don't necessarily work with just a Kobayashi hyperbolic manifold, but we work with a negatively curved manifold.
So Kyle, can I ask you a question?
Absolutely.
So if you drop the background Kähler assumption for surfaces, is it known, or
so the question is whether a compact Kobayashi hyperbolic surface, possibly non-Kähler, does that admit a Kähler-Einstein metric of negative Ricci? Yeah. It's a very good question. If the second Betti number is less than or equal to 3, yes. Less than 3, the 3 case may be borderline. If its second Betti number is bigger than or equal to 3, you need to assume the global spherical shell conjecture, because the class 7 surfaces with B2 bigger than or equal to 3, we don't know what those are, but if you assume the global spherical shell, then there are exactly B2 rational curves, so they can't be hyperbolic. So, yeah.
I see. Okay,
that's
thanks.
a good question, yeah. Okay, so to get into the curvature aspects and the specific case of negatively curved manifolds and their canonical bundles, let's take X again to be a complex manifold. Take it to be compact if you want. And suppose that G is a Hermitian metric, and I can locally write it in this form. So I have this locally defined Hermitian matrix valued function, which is weighted against this DZK, DZL bar. The curvature tensor of the metric is then locally described in this way. So it's the components of the curvature are locally described as minus the complex Hessian of the metric plus this first order term. If the metric is Kähler, then you can just think of this as the ordinary Riemannian curvature tensor. But if the metric is non-Kähler, we've already seen that the complex structure is not preserved by the Levi-Civita connection. So it's replaced by the so-called Chern connection, but the details of that are not so relevant for today's talk. And now we have the actual definition of the holomorphic sectional curvature, which is given by the curvature acting on, let's say, a locally defined holomorphic vector field in this way. So as I said before, if you're more comfortable with Riemannian geometry, one can think of this, let's say for a Kähler metric, as the restriction of the sectional curvature to the 2 planes which are invariant under the complex structure. So the holomorphic sectional curvature is mysterious, but one thing we do know that it does is it controls the value distribution of holomorphic curves in the manifold. So we've already seen that if we have a complex manifold with a Hermitian metric of strictly negative holomorphic sectional curvature bounded above by a negative constant, then every holomorphic map from C is constant, so we don't have any holomorphic curves. If the manifold is compact and there's a Kähler metric of positive holomorphic sectional curvature, then this is a result of Yang that the manifold is rationally connected. So in fact, there are so many rational curves, or at least sufficiently many flexible rational curves, such that any 2 points can be contained in the image of a holomorphic map from CP1 into the manifold. On the other hand, the holomorphic sectional curvature is not strong enough to control the Ricci curvature. So in particular, there's a result of Hitchin in 76, which shows that if you look at Hertzebruch surfaces, these are P1 bundles over P1, then for n bigger than 1, they all admit Kähler metrics of positive holomorphic sectional curvature, but if n's bigger than 1, these aren't Del Pezzo surfaces anymore, so they can't have Kähler metrics of positive Ricci curvature. But so we see that positive holomorphic sectional does not imply positive Ricci, but we have this rather surprising, curious conjecture that's a special case of Kobayashi and Lang, which was made by Yao in the 70s, which predicts that if we have a compact Kähler manifold with a Hermitian metric of negative holomorphic sectional curvature, then the canonical bundle is ample. And so in particular in particular, the manifold's projective, and then by Orb and Yao, there's a Kähler-Einstein metric of negative Ricci curvature. So this is curious because it's not necessarily the same metric. We're not saying, of course, that the negatively curved metric is Kähler-Einstein, but having a negatively curved metric on our compact Kähler manifold forces some other metric to have negative Ricci. So there's this asymmetry in the sign preference of the holomorphic sectional. So this form of the conjecture is what has received the most attention lately. So the conjecture was verified by Haya, Liu, and Wang in 2010 for projective threefolds endowed with a Kähler metric of negative holomorphic sectional curvature. So here we see that the structure of the argument uses a lot more machinery from algebraic geometry. The general strategy was developed by Wu Yao in 2016, and they were able to show that a projective manifold of any dimension endowed with a Kähler metric of negative holomorphic sectional has a Kähler-Einstein metric of negative Ricci. That's the projective assumption makes use of Maury's cone theorem, which is a very strong result in algebraic geometry, which is far from known for compact Kähler manifolds in general. It's known in dimension 3 only. But the remarkable achievement of Tassati and Yang the following year was they were able to show directly that the existence of such a negatively curved metric can be used to bypass the Maury theorem altogether. So as a consequence, the culmination of Haya, Liu, Wang, Wu Yao, and Tassati Yang yields the following theorem, which is typically just referred to as the Wu Yao theorem. So a compact Kähler manifold, X, with a Kähler metric of negative holomorphic sectional, has a Kähler-Einstein metric of negative Ricci curvature. Now, the Wu Yao strategy is to proceed by contradiction, assuming the canonical bundle is ample.
Sorry, Kyle.
And then,
another stupid question. Can you go back one slide, please? So there's a conjecture here by Yao.
Mm-hmm.
And this is still open in full generality.
Compact Kähler with a Hermitian metric of negative holomorphic sectional.
I see so the difference is that the theorem assumes that the metric is scalar. The same
Exactly.
sort of, the metric with negative curvature is the one making it scalar. Okay. That's the
Yeah.
only sort of,
That's
okay,
the only distinction in the, yeah. In a
thanks.
later slide, you will see something very similar to this, and I underline them, but I should have underlined them here.
No,
So-
that's all right. Thanks.
Okay, so the Wu Yao strategy is to proceed by contradiction, assuming the canonical bundle is not ample. From there, the idea is to produce a sequence of Kähler metrics, preferably with a Ricci curvature lower bound that satisfies these properties, and then obtain uniform estimates which are independent of this flow parameter epsilon, and that's used to obtain the desired contradiction in the same way. It's a kind of standard compactness contradiction argument. So if G hat is the Kähler metric with negative holomorphic sectional curvature, the core estimate to obtain is to bound G hat by some multiple of these flow metrics, or equivalently, bound the trace of G hat with respect to G epsilon by some uniform constant C. The reason why this is the main estimate is once you have this, you can kind of go through the standard Yao machinery that goes back to Yao's resolution of the Kobayashi conjecture and get all the estimates in the standard way. So the main technique for obtaining this estimate is the Schwarz lemma. So this is equally interpreted as an estimate on the derivative of a holomorphic map, since I can write the pointwise square norm of the derivative of f as the trace of the pullback. And in every application, including this one, we take f to be the identity map, but it makes the estimates look a little cleaner if we just let the identity map be denoted by f and proceed in general. So that's what I will do here. So we'll write f for the identity map, and f is a holomorphic map with the source metric being G epsilon and the target metric being G hat. I can locally write the derivative as Fi alpha dzi tensor the pullback of dw alpha, where Fi alpha is the ith derivative of the alphth component of f. Now, Liu in 1967 carried out the following general calculation. She showed that if you work with the G Laplacian, so you take the complex Hessian and then trace it using the metric on the source, here G is G epsilon, then you end up with the following three terms. You end up with the pointwise square norm of the second fundamental form, more or less. You end up with a source curvature term, which depends on the Ricci curvature of G. And then you end up with this complicated target curvature term. Now, it's actually kind of, you can get a kind of intuition for why this calculation goes this way by thinking of a kind of elasticity analogy, which is sometimes done in harmonic maps. So you imagine you have a material on a given surface that's sitting in elastic equilibrium, and you want to transport it to another surface and then make sure it determine the conditions under which that will remain in elastic equilibrium. What's going to affect that is, well, the ground state you're starting off on, well, that's like if it's in elastic equilibrium to begin with, well, then the ground state is affecting that. And how do you determine the ground state? Well, it's going to be the curvature in all the directions and then an average of that. So that's why we get this Ricci curvature term appearing. The next thing that will impact it is the curvature of the target. If you put it onto something that's very negatively curved or something, that will put a lot of tension on it. So that's exactly what we see here, this target curvature term. And there's only one thing that could then affect how this material is sitting on the target manifold, and that's how it's sitting in there. In other words, the submanifold geometry, and that's encoded in this second fundamental form. So it makes sense that there are three factors in this calculation. So to get estimates on this thing, though, we want to apply the maximum principle, which we don't have to use any fancy machinery for since the manifold's compact. But we need to get a lower bound on this source term. In other words, we want a lower bound on the Ricci curvature of G. And we want an upper bound on the target curvature term of G hat. So that's the name of the game in order to get a nice estimate on the trace. So since Liu's calculation in 67, there have been two general improvements on this calculation. Now I'm using the term general improvement very precisely. There have been, the Schwarz lemma is one of the main techniques in Kähler geometry, so a significant number of people have worked on it and made it work for a particular context. I'm not talking about extending this to Kähler-Ricci flow or having some auxiliary structure that I can squeeze more out. I'm only talking about this calculation in the level of generality of holomorphic maps between Hermitian manifolds. I argue that there has only been two improvements in this case. The first is due to Yao in 78, who applied his generalized maximum principle to this calculation, and that allowed for the compactness condition to be dropped so long as you had a complete metric with a lower bound on its Ricci curvature. The second improvement is due to Royden, who showed that this target curvature term can be controlled from an upper bound on the holomorphic sectional curvature if the target metric is Kähler. And so Yao's theorem allows us to apply the Schwarz lemma to more general source manifolds, while Royden's allows us to apply it to more general target manifolds. How this concretely manifests in the estimate is the following, but the details are not too important here. So this is Royden's Schwarz lemma. This is the main estimate that is at the core of all these Wu-Yao theorems so far. So we have a compact complex manifold, complex dimension n. Suppose we have a holomorphic map with G, the source metric, G hat, the target metric. I suppose that G is Kähler and it affords this lower bound on its Ricci curvature. This doesn't assume a sign on its Ricci curvature, for instance. And I suppose that G hat is Kähler with the holomorphic sectional upper bound, let's say bounded above by a non-positive constant. Then the estimate you end up getting is of this type, but when applying the maximum principle, you get the desired estimate you like. Okay, now I'm not expecting anyone to really understand the significance of this. It does take some time to really see it, but one thing I'll add is that this is exactly what we see in harmonic maps. This Laplacian of the energy density, this is the same thing, where harmonic maps are replaced by holomorphic maps and so forth. So recall that the main application, at least for this talk, of Royden's Schwarz lemma is this theorem of Tosati, Yang, and Wu-Yao, that a compact Kähler manifold with a Kähler metric of negative holomorphic sectional is projective with ample canonical bundle and therefore has a Kähler-Einstein metric. The main goal is this conjecture of Yao, which is in particular a conjecture of Kobayashi and Lang, which predicts that a compact Kähler manifold with a Hermitian metric of negative holomorphic sectional has ample canonical bundle. Now, anyone in complex geometry will tell you very, very quickly that if you try to drop the Kähler assumption to Hermitian, good luck. It is very difficult in general. And as a consequence, this has inspired the introduction of a large number of classes of Hermitian metrics which generalize the Kähler condition in some way, trying to bootstrap our way out of the confines of Kähler geometry. And while I can tell you about, a large number of these, for today I'll only bother you with one of them, and those are the pluriclosed metrics. So instead of mandating that this 2 form is closed in the sense that d omega is 0, that's what the Kähler condition is, we only require that dd bar is closed. So this kind of particular component is 0. Such metrics, in contrast to Kähler metrics, these always exist on a compact complex surface. In fact, there's a unique one in each conformal class of a Hermitian metric on a compact complex surface. And since this is a geometry with symmetry seminar, let me at least mention one Lie group that's present. If you look at the bi-invariant metric on a compact semi-simple Lie group of even rank, then this can be endowed with a complex structure, which is due to Samuelson, and that will be a pluriclosed metric. So these are a natural class of Hermitian metrics to consider, and there's many, many reasons to consider them, but that's about as far as I'm going to. Well, there'll be a later motivation that we'll see in a moment. So in these Wu-Yao theorems and whatnot, the negatively curved metric is used in one place and one place alone, and that's in the Royd-Schwarz lemma. There's no other place it's used. But unfortunately for non-Kähler metrics, Royden's argument breaks down. It's unfortunately a false belief that perpetuated for about 40 to 50 years that Royden's argument, or 40 years, Royden is 1980, that it held in general, but that's not true. And this was really settled definitively and put straight by Yang and Zheng in 2018 when they introduced the real bisectional curvature. So this is where we don't look at 1-0 vectors, we look at Hermitian 1-1 tensors. So it's a stronger condition than the holomorphic sectional curvature, but it coincides with the holomorphic sectional, or is comparable to the holomorphic sectional if the metric is Kähler. Now, this is defined to be exactly the target curvature term in the Schwarz lemma. So, of course, you naturally get a Wu-Yao theorem out of this. You know, you assume a compact Kähler manifold with a Hermitian metric of negative real bisectional curvature, well, then it has ample canonical bundle. That's because you've essentially introduced the obstruction, and then you, of course, get theorems once you assume the obstruction is okay. But now we're in a very difficult situation because Yao's conjecture predicts that, or requires that the metric is Hermitian non-Kähler. Now, to proceed with the standard strategy of using the Schwarz lemma, we need to handle this target curvature term. But Yang and Zheng have made it very, very clear that that's not possible. In fact, they've essentially shown the real bisectional curvature is sharp. They've taken the target curvature term, defined that as the real bisectional. So how are you going to do any better? You can't. I mean, this is the state of affairs. But what's surprising is that that's actually not the case. It turns out the real bisectional curvature is not sharp, and James and I figured out a way of dealing with this. And so this is the first general improvement on the Schwarz lemma, general in the sense I described earlier, general improvement on the Schwarz lemma in the Hermitian category since 1980. Now, before getting you to sign all the papers and convince you of the technicalities of the result, let me sell it to you. Let me sell you the main product that we're offering. So this is the main theorem. We have a compact Kähler manifold with a pluriclosed metric of negative holomorphic sectional curvature. Then the canonical bundle is ample, the manifold's projective, and there's a Kähler-Einstein metric. So this is the first instance where we're able to use the holomorphic sectional curvature of a natural class of Hermitian non-Kähler metrics. So this is, I mean, if you asked me, maybe 6 months ago whether such a result's possible, I have no idea. It's absolutely, and we kind of stumbled across this, admittedly. So how do you do it? Well, it's like a lot of things, it's obvious once you know how to do it. Problem is not knowing how to do it. So the core idea is to look at this good term, this pointwise square norm of the second fundamental form. This is a term that's got a, it's non-negative, so doesn't affect the estimates. And so people often ignore it. But the core idea is that if you pull out the skew symmetric part and the target metric is not a Kähler metric, then what arises are torsion terms which temper the real bisectional curvature term. In other words, they can be used to relax the curvature requirement on the target. So as a consequence, we obtain the following general Schwarz lemma. So we take a holomorphic map between Hermitian manifolds, then we obtain this estimate here. So we have this source curvature term. That's the same one that we had before. We're assuming the source metric is Kähler. Then we have this additional quadratic torsion term, which is, if you assume a sign on this curvature term, that's weaker than real bisectional curvature. So it is an improvement. And since this quadratic torsion term tempers the real bisectional, it seems natural to refer to this as the tempered real bisectional curvature. Now, this is intrinsic to the Hermitian structure in the sense that if you look at the complex Hessian of the metric in geodesic normal coordinates for the Chern connection, the natural connection, then this is the second order error term that appears. And so this is the quadratic form associated to that second order error term. But even more remarkably, one can show that if the target metric is pluriclosed, then negative holomorphic sectional actually implies negative tempered real bisectional curvature. And so with these two ingredients, we obtain the first general Schwarz lemma that goes beyond Royden for an honest class of non-Kähler Hermitian metrics. And in particular, that's how we obtain this theorem of Wu-Yao type. So I think I'll stop there. Thank you.
Thank you, Kyle. Very nice result. Are there any questions or comments for the speaker? Well, I mean, I'm forced to ask, right? Is there any hope to go beyond pluriclosed? What would be
Absolutely.
the next step, so to speak, before the general Hermitian case?
I have no idea. I'm hoping, I mean, James can attest to this. We did not come up with, pluriclosed is the natural step. We didn't have any insight ahead of time onto these things. They kind of just fell out. So, I mean, that's what research is, right? If you know the answer ahead of time, know how to do it, then it's really just labor. I'm suspecting that working with something that maybe K-Gordachon metrics, which kind of, when K is 1, you get a pluriclosed condition. Astheno-Kähler metrics are the other extreme.
How about balanced, which is sort of the opposite of pluriclosed in a
Balance
sense?
doesn't do anything. If balanced for me is a source curvature condition, not a target.
Well, but I mean,
condition.
it's still a Hermitian metric, right? So you need to have
Of
the
course,
theorem for
but,
balanced metric. So.
Of course, but I don't think you will get something like this. I would be very surprised if someone can prove that a compact Kähler manifold with a balanced metric of negative holomorphic sectional is projected with that. Like the balance condition, it's a trace type condition.
I mean, regardless of what type of, it's still a particular case of the general problem, right?
Of course, absolutely. But I think if you
Um,
could do it for balance, you could probably do it for Hermitian.
well, there you go then.
To
That's
me.
a good
But
next
I
step.
don't. Kähler is so when you require dd bar omega to the n minus 2 to vanish, that's a natural thing that appears on the target. I mean, they were introduced because they arose in the target curvature term for Hermitian harmonic maps. But I'm not sure. If anyone has any ideas, please let me know because I'll happily have them.
Are there any further questions or ideas for the speaker? Well, I mean, if not the case, then let's thank Kyle again for a very nice talk.
Thank you.